Welcome to Learning Intention 2, Describing Datasets. In this video, we're going to have a look at developing our understanding or mathematical notation in describing something called a dataset. Now, we're taking a slight deviation from the statistics area that we've been in, and we're moving over into a little subsection called set theory. Now, this in itself, the size of the map doesn't do it justice, as this is a huge topic, but we're just going to skim across the surface and get some tools from here to help us represent our data over in the statistics and probability section. So consider a problem where you've got two different types of dice. You've got an icosahedral die and you've got an octahedral die. And you want to be able to represent all possible outcomes of each die respectively using mathematically correct notation. And then secondly, what we want to do is we want to be able to express the commonality between both dice. So right now we don't quite have the tools in our toolbox to be able to do this in a universally accepted mathematical convention. But we're going to get some tools or learn some notation today that will allow us to do this. So this is where we come to describing data sets. So firstly, what is a data set? Well, according to Wikipedia, in mathematics, a set is a well-defined collection of distinct objects considered as an object in its own right. So what could that look like? Well, there were three I could think of. So the most trivial ones were the numbers of a cube die. So 1, 2, 3, 4, 5, and 6. So notice all of these possible outcomes if we throw the die of a cube, or if we throw a cube die, it could land with any one of these numbers facing upwards. So all of these numbers put together and described in this curly bracket, that's a set. Another experiment we could do could be a coin flip. So the two possible outcomes could be either heads or tails. And we can write that as a set as in curly brackets or braces, heads and tails. And the final one I thought of was outcomes of a football match. So you could either win, you could have a draw, or you could lose. So these are three possible outcomes that you would see in a football match. Now let's have a look at some of the notation for a set. So over here we've jumped over and there's some really strange symbols. So the first one, it sort of looks like an E. So this symbol means element of. And what you can do is you can use this symbol to denote whether a particular item is a member of a set. The next one is not element of. So notice it looks almost identical to element of, except it's got a dash struck through it. The next one is braces with nothing inside it, or like an O with a dash in it. This means empty set. So it means there's a set and there are no items or members within the set. And the final bit of notation for this slide is set length. So it's N, and then in parentheses you've got an S. The S representing the set in question, and the N representing number of. So this represents the amount of items or members within a specified set. Now looking at a dice example, if we have a square die or a cube die, the possible outcomes could be in braces 1, 2, 3, 4, 5, or 6. And if we're going to use our notation from before, so element of and not element of, we can see in this first line that 1 is an element of set P. Set P representing the amount of outcomes or the different outcomes that you could have if you tossed a cube die. Going one line down, 7 is not a member of. P. So if you toss a die, you can't get an outcome of 7. And then finally on the third line here, we've got N and in parentheses P. So what this is asking is, how many members are in the data set P? And simply by counting 1, 2, 3, 4, 5, 6, there are 6 members in this data set. Awesome. So moving on, we've got another notation and subset. So what is a subset? A subset is a set where all the elements are also present in an even bigger set. So consider sets P and Q. Set P has members 1, 2, 3, 4, 5, and 6. And set Q has members 3, 4, and 5. Because all of the members in Q are present in set P, we can say set Q is a subset of set P. So this particular video, it's quite dense in a lot of new notation, but we've only got a little bit more, and then it will be out of the way. So the next part is notation of intersection and unions. So an intersection is a comparison of the commonality of two sets. So you're asking yourself, what is common across two different sets? So considering sets P and Q over here, so set P has members 1, 2, 3, 4, 5, and 6. Set Q has members 1, 3, 4, and 6. And this little symbol here, it's almost like an upside down U. It represents what is common, or it asks the question, what is common between set P and set Q? And looking at this, we can see that 1, 3, 4, and 6. So 1 is in both sets P and Q. 2 is not in set Q, so it's excluded from this list here. 3 is common in both sets. And 4, that's also common. And finally 6 is common. So the ones that aren't common is 5 and 2. Going down, we've got union. So union means the merger of two different sets. So if we've got set S and set R here, this should be set S, this should be R. Then the union of set S and set R is the merger of all of these, or all of these items in both lists. So we're going to have R equals 1, so 1 appears here. 2 is common across both of them, so it still appears anyway. 3 is in R but not in S, but because it's a merger or the union of two sets, then 3 gets included. And we go all the way through until we've had every occurrence of an item in either S or R appears in the union of S and R. And finally, the final piece of notation in this particular video, we've got mutually exclusive. So exclusive being that something only appears once. So two data sets can be described as mutually exclusive or disjoint if they share no common elements. This can be represented mathematically as P and Q. So the intersection of P and Q has no common elements, or it has an empty, it creates an empty data set. So remember, this symbol here, the O that's been dashed out, where are we? Here it is. It represents an empty set. So the intersection of P and Q has no common elements. So we could write it like that, or we could write it like that. But I'll keep it at that for now. So consider sets P and Q. In P, it's got items or members 1, 2, 3, 5, and 7. And Q has 0, 10, 20, and 30. And we ask ourselves, what is the intersection of P and Q? Well, they have no common elements. Therefore, P and Q are mutually exclusive. So that concludes all of the new notation that we're going to use for now. So let's go back to our original question of the dice. So you have an icosahedral and an octahedral dice. The numbers on the icosahedral and the octahedral dice range from 1 to 20 and 1 to 8 respectively. How can you, 1, express all the possible outcomes of the dice, and 2, express the commonality of both die mathematically? Well, we can do this using sets. So going down, P representing all the outcomes on the octahedral die is 1, 2, 3, 4, 5, 6, 7, and 8. And the icosahedral, so that has 20 faces. So I wrote 1 all the way to 20 in this set. And P and Q, so this little section here, that represents question 1. Now question 2, express the commonality of both die mathematically. Well, what is the intersection of P and Q? Well, it is simply 1 all the way up to 8. So we've excluded 9 to 20 because on the octahedral die it only goes 1 to 8, and what's common between the two is numbers 1 to 8. So this is how we'd express the possible outcomes and the commonality of both die, or outcomes of both dice, using sets. So in conclusion, today what we learned was sets and the mathematical operations and notations of sets. And secondly, we learned how to represent outcomes using set notation.